Okay, so I need to give you guys a new tool. This thing is cool. So here you're getting a thing called Green's theorem, which is very neat. And what it does is it takes line integrals and turns them into area integrals, which seems, I know, totally insane, and is, in fact, totally insane. So what I need for a little setup is I need to let C be a positively oriented curve. Now, let's toss piecewise smooth in here too. So C is going to be a positively oriented, piecewise smooth curve in the plane. Ooh. Sorry. We need a piecewise smooth, simple curve. I know a lot of these words don't mean anything yet. We'll get there. In the plane, and let D be the region bounded by C. If P and Q think functions of x and y have continuous partials on an open set containing D. Oh my God, I'm getting tired of writing. Then, punchline, ta-da, the line integral over C of P dx plus Q dy is the same thing as the double integral over the domain D of the partial of Q with respect to x minus the partial of P with respect to y integrated with respect to area. Okay, now, new color. We need to unpack some words, right? Okay. C is a curve at least, right? Are you guys on board with what a curve is?
I thought it was a constant.
Okay, so what's a curve?
It's
I love this. So everyone's on board with a curve, and you're all like, uh-huh. So what's a curve?
Some parameterized function.
Oh, function.
Good. It's a parameterized, right? It's a parametric function that. Ooh. Whose image is in the plane, right?
Yeah.
You guys see this? So for C, what I'm really thinking is kind of the graph of an R of T, right?
Okay.
I don't have a better color. Okay, so C is the graph of something, right? Of some parametric curve. What does positively oriented mean?
It's not going. Yeah, it's just kind of.
What did I tell you mathematically positive was? Just like. Okay. So that's counterclockwise. What's piecewise smooth mean?
Is that referring to the continuous behavior of the parameter?
Yeah. So piecewise smooth allows for finitely many sharp corners or cusps or whatever. Right? So the smooth part, if I left off the piecewise smooth, if I just said smooth, that would allow for no sharp corners or cusps or whatever. The piecewise part lets me put in finitely many at least of those. You guys cool with this?
Oh. So you have a.
Okay. What's simple mean? This might be a new word.
I mean, we kind of all grasp what it means, but like describing how
I
it's.
frankly have no idea.
Okay, good. It's better that you think you don't know what simple means.
Yeah.
Simple means very specifically that it's non-self-intersecting.
Oh, okay.
That's a bit.
So every input has a single output, kind of.
Every
every
output
output
has
has
a
a
single
single input to get
input.
there.
Yep.
Yep.
And why do I not? Oh, I missed a word. That's why I don't have the right word. I need to add the word closed. What is a closed curve?
Returns to its point of origin.
Yeah, okay. Think a loop. Right, it comes back to where it started. You guys good with this? So far on my curve, I have qualified that it's the graph of a parametric thing, right? That's what a curve is. It's piecewise smooth, which means it has finitely many corners. It doesn't intersect itself. It makes a loop, and that loop is counterclockwise oriented. Guys all good with this?
Yep.
Why did I need the closed part? Because I needed it to bound a region, right? Also, I needed for counterclockwise oriented to make any damn sense at all. You see that? Like, if my curve looked like this, is that one counterclockwise oriented or clockwise oriented? I don't know. Right? So let me just throw up some non-examples of curves and some examples of curves just so we're all on the same page. You guys good with this? So a non-example, what's this one's problem?
It doesn't close.
Yeah, it's not closed. What's this one's problem?
It crosses.
Not simple.
It's not simple.
And it's not.
I have no idea whether this is counterclockwise or not. It's clockwise on that part and counterclockwise on that part. You guys all see that?
Yeah.
You could separate them.
Right? Like if you push this around, that's weird. You guys good with that?
Mm-hmm.
Okay, so this one is not simple. This one is not closed. Let's see. What if we just did this and oriented that way?
Oh, that one's not
Yeah, this one's negatively oriented. How could you fix that?
reverse orientation, or just make it.
Yeah, or just flip the sign when you get to the end.
Yeah.
You guys all good with that? Okay, that one at least is an easy fix. Let's see, what else did I miss? Oh, piecewise smooth. So here's an example of a curve that's not piecewise smooth. You have to, so bear with me because I'm going to have to erase some stuff here. So you start with a triangle, and then in the middle of the triangle you do this,
Oh god.
and then in the middle of those triangles you do these.
Oh my gosh, one of these things that ever. The endless ones?
Yeah, this is a fractal called a snowflake curve. And then go around in each of those triangles, or in each of those line segments, and put another triangle in the middle of it. And then do that again, and do that again, and do that again, right?
It's infinite.
And then take the limit of that process, and you'll get some curve in the plane, but that curve will not be piecewise smooth. You guys see that? Because it's clearly going to have infinitely many corners. This curve, as it stands, where I've done 2 steps worth of that, is this piecewise smooth?
Yes.
Yes. But the limit of this process isn't. So I'm going to just put limit of that. Cool? Not piecewise smooth.
That's actually interesting. I mean, is there a way to prove that it's not smooth in the results?
Yeah, but it takes a lot of analysis.
Because I wouldn't intuitively just assume that it's
Yeah.
smooth taken to the limit.
Yeah, that's a totally fair point, right? In a limit, you could get something smooth out of this. It turns out you don't. That's hard to prove. You guys good with this? So there's other ways to make similar kind of broken-y things out of fractal processes. Or you could conjure up some other ways to make things that aren't piecewise smooth, but I think you're going to have a hard time drawing any of them. Guys good with this? Examples of shapes that actually work. They basically all look like a little potato that's counterclockwise oriented, right? You guys cool with this? Okay. I assume that you all can draw potato-looking things.
Triangle's cool, right?
Yeah, sure. So triangles are fine. Squares are fine.
Roller coasters are fine.
Things that are inconvenient are fine. Right, like funny little chevrons or whatever. They don't have to be convex, right? So you can do this too with roundy things.
They just can't cross.
Yeah, they just can't cross. Don't do screwball roundy things. So if you take limits of roundy things, they also don't necessarily work. So if you took, for instance, kind of a funny potato thing that like reached out at itself, and then you did something where you like
Have them get closer and closer to this.
split it into bits, like, I don't know, maybe we'll make it go like this, and then we'll put this thing further in there or something. And then we'll split it again into little bits to more entangle these.
So basically, when there's a limit, it's probably not.
Yeah, you need to think harder about it if you do some kind of limiting process like this weird tentacle monster, right? So that one goes in the non-example side. So you have to be really, really careful with those things. But on the upside, they're hard as hell to parameterize anyway. And the boundaries of those shapes are hard as hell to find, right? So you're not going to be doing this anyhow with a shape like that, because you're not, like, parameterizing the curve isn't going to be an option, which you need to do to get the line integral. And getting the edges of the domain, right, also not going to be a real option. So you're going to have a hard time even computing these things anyhow. Does that make sense? You guys cool with that? Okay. If you want to rewrite these a little bit, you certainly can do that, right? You guys see that this is my kind of, this is the way I told you that I don't normally write things, right? Normally I would write this as the integral over C of f dotted with dr, right?
Oh, so okay.
You guys good with that? Where the components of f are p and q. You guys cool? That guy, of course, is actually the way I write that normally. This business here, right, is what kind of object? That partial of q with respect to x minus partial of p with respect to y? What category of thing is that going to be?
Still gonna be
Okay, yeah, it's the curl of something, but you don't know what that word means
it's
yet.
a
so
function.
Yeah, right. P and Q are functions of x and y, right? They're the components of a vector field, so they're a function of x and y. And then I took a derivative of each of them, right? A partial.
Yeah.
That's still going to be a function of x and y. And then I subtract.
That's
Right.
still a function.
So categorically, this thing here is a function of x and y. You guys see that? Yeah, it's a weird function. But it's really just a scalar function. I'm adding it up. You guys see this?
So wait, when it says functions of x comma y, like when you say that p and q in the little, does that mean like q? Yeah. Are you kind of saying that like p is all the x's and q is all
No, no. So this might be p as a function of x and y, right? And q as a function of x and
the?
y.
Okay.
So this looks like.
It's just that this is the x component of a vector field, and this is the y component of a vector field.
Okay.
So there's no t's. We don't need to parameterize when we do this, do we?
You're going to have to parameterize because that's how you execute a line integral.
Okay.
Does that make sense? You guys all see that?
I mean, I'm sure actually it would make more sense.
Because to actually do an integral over a curve, you need to, your first step is parameterize the curve and then plug in. You guys want to try one of these?
Yeah, I think I'd
Yeah.
want to learn more from just staring at it for a bit.
Okay. So let me turn this on.